Hi, I'm Asmita Chapagain, and I'm going to discuss about does a whole planted cover crop impact soil fertility management. Let's start with soil fertility. It is the ability of soil to sustain crop growth and development. What makes the soil fertile is the availability of essential nutrients and the lack of toxic elements. So, how do we maintain soil fertility? Soil can be made fertile by adopting practices that add nutrients to the soil, as well as by following practices that actually help prevent the loss of nutrients. Soil fertility management practices are common and as simple as addition of manure to the field or the addition of inorganic fertilizers. The soil fertility can as well be maintained by irrigating the field because it helps augment the soil moisture to a level preferred by the specific crops. Soil fertility can also be managed using some sustainable techniques like the application of cover crop. Cover crops are simply the crops covering the surface of our soil. They help manage soil fertility by adding moisture to the soil, supplementing nitrogen to the soil, maintaining diversity of soil biota, sequestration of carbon, helping to control soil erosion, minimizing soil compaction, improving soil aggregation, and regulating soil temperature. Although not all the methods listed here do increase the nutrient contents, but surely they lead to a greater availability of nutrients to our crops. During the winter, when the temperature drops down below freezing point, soil is covered with snow. During that period, the growth and development of our plant is halted. In such a case, plants essentially do not require any nutrients when they are affected, especially by frost. So, do our soil retain all the nutrients during this dormant period? To evaluate this, we conducted an experiment to evaluate the need for spring fertilizer reapplication following fall planted cover crop. The experiment was conducted in Kimberley Research and Extension Center, located at an altitude of 3,924 feet. The region has an annual precipitation of 9.42 inches. The soil is in the order arid soil, and the climate is semi-arid in the region. For the experiment, we used randomized complete block design with 10 treatments and 6 replications. Our control was a fallow with no irrigation as well as no fertilizer. Irrigation and fertilizer were our two factors with low, medium, and high levels of each. For field preparation, we performed tillage using a Mouldboard plough. After that, we applied glyphosate, commonly known as Roundup, as a broad spectrum herbicide to control weed. We used urea having 46% of nitrogen as our fertilizer. Low, medium, and high level of fertilizer was maintained at 0, 45, and 90 pounds per acre of nitrogen. After fertilization, round harrow was used to distribute it evenly throughout the field and also to level the land so it will be easier for us for cultural practices. The seeding was done with a mixed cover crop seed. For rapid germination, irrigation was applied to all the treatments equally at the initial phase at a level of 1 inch approximately. After that, low, medium, and high level of irrigation was allotted at 14, 10, and 7 days interval respectively. The plantation date of the cover crop was September 16 of 2019, and the day of first frost was 14th of October. So you can see that we only had a small window period for our cover crop to actually grow. The first sampling was done on fall 2019 after first had frost, whereas the second sampling was done in the spring of 2020 before the cover crop started growing back again. We used bucket auger for sampling the soil. After that, the samples were analyzed in the lab for salt, ammonium, and nitrate concentration. The data we obtained was then analyzed using SAS. ANOVA was performed for all sets of data. Here in the table, you can see the list of data analyzed and the sections where they were significant at the level P lesser than 0.05. In the figure where the tick mark is present, the data was statistically significant as at P lesser than 0.05. None of the components were significant for the interaction of treatment and time, so we would not be discussing this in our presentation. Electrical conductivity, nitrate, and plant available nitrogen was significant for treatment as well as the time, but ammonia was not significant for any. The graph you can see now is the graph for the average electrical conductivity among the treatments. Similar alphabets at the top of the graph denote no statistical difference. From the figure, there is no clear group distinction among the treatments. The graph you can see now is the graph for average nitrate concentration among the treatments. The alphabets in the graph separate the group on hierarchy. Similar alphabet means statistically same level. Here B is superior to A, or B has the highest average nitrate concentration than A. This graph shows the average plant available nitrogen. Here, when we say plant available nitrogen, we are talking about the combination of ammonium and the nitrate. Similar alphabets mean that the two groups are statistically at par or are at the same level, and B is superior to A, means B has the higher plant available nitrogen than A. This graph over here shows the difference in electrical conductivity between the fall of 2019 and spring of 2020. The fall is superior to spring with higher electrical conductivity, thus higher salt concentration. The next graph over here shows the average nitrate concentration as well as the average plant available nitrogen concentration in between the fall of 2019 and the spring of 2020. It is clear from the graph that both the concentration of nitrate and plant available nitrogen was greater in the fall of 2019 than that of spring 2020. Although ammonium was not significant for anything, in one of the treatments, the ammonium concentration was higher than that of the fall. although the treatments were statistically the same. So, what actually caused the decrease in nutrients over the winter? The answer is leaching. As you can see from the figure, the clay particles have negative charge in them. They strongly attack the positively charged ammonium, whereas repel the negatively charged nitrate. This is the reason why ammonium doesn't leach out, because it is strongly attached to the clay. But our nitrate do leach out when there is water available. And that's why the nitrate concentration was greatly reduced in the spring than that of the fall. In the case of salt, the basic radical, although having the positive charge, is weakly bonded to the clay particles as it forms ionic bond rather than a covalent bond that are easier to break in a solution. Acidic radicals in the salt are positively charged. The salts, when comes in contact with water, dissolves in it rapidly and leaches out. Leaching is also the reason for water pollution in underground or the groundwater. So we can conclude that no matter the amount of fertilizer we apply in the fall, the nutrients are leached out and are not available for our next cash crop. Fertilizer reapplication becomes necessary at this point. The application of fertilizer in the fall, just prior to the frost, only means loss in the investment and the salts, nitrate, and all the money, and everything ends up in the drain. The leaching of the nutrients also leads to water pollution. So higher the fertilizer used that gets leached, more the chances of polluting the groundwater. Although there was difference in irrigation level, it was not proportional to the loss of nutrients. So more water doesn't always mean that more of the nutrients are gonna get leached out. And more fertilizer in the fall doesn't always mean that more fertilizer is available to us uh, in the spring. This is all. Thank you.